In this video, we're going to be looking at the improper integrals of the second type, where we have our integrand being discontinuous at some point in our interval. So if we have our function being continuous on the interval from a to b, so it's continuous at a all the way through the interval, but then discontinuous at b, then in order to compute the integral from a to b of f of x dx, we rewrite this as a limit, and we'll be making use of a one-sided limit. In particular, I'm going to replace that problem value here of b with some variable t, and then I have to think about what happens as t approaches b from inside of the interval, so that'll be a limit as I approach b from the left of f of x dx. Okay, and then similarly, if I have my function being continuous on the interval from a to b, but discontinuous at that left endpoint at a, so the problem value here is at a, I'll rewrite this as a limit as t goes to a from the right of the integral from t to b of f of x dx. Okay, and then we have the same terminology that we used before, where we'll say that the improper integral converges if that limit in either one of those cases exists, meaning as a finite number. Okay, and we'll say that it diverges otherwise. Okay, so remember, if the limit doesn't exist, or if the limit comes out to be infinity or negative infinity, we'll say that the improper integral diverges in that case. So the two definitions that we looked at so far was cases where there was a discontinuity at an endpoint. So what if there's some point where the function is discontinuous in the middle of the interval? Well, in that case, we'll write our integral here as an integral from a up to that point where there's a discontinuity. So an integral from, let's say, a to c of f of x dx plus an integral from c to b of f of x dx. And then we'll have to look at approaching c in this first integral from the left and approaching c in the second integral from the right. So I'd have something like the limit here as t goes to c from the left of an integral from a to t of f of x dx plus a limit as, let's say, r goes to c from the right of an integral from r to b of f of x dx. Okay, and then similar to the case where we were looking at a limit between negative infinity and infinity, and we had to break it up into two pieces, we'll say that the integral converges if both of those integrals converge, and it will diverge if at least one of those pieces diverges. Okay, so whenever you have a situation where you've noticed that there's a discontinuity in the middle, you'll write it as these two separate integrals. And then you can just look at evaluating one of them to start with, see whether that integral is converging or diverging. If it converges, you go ahead and compute the second one. If it diverges, then you know you're done, because if at least one piece diverges, then this integral over here will be said to diverge. So let's look at our first example of one of these types. So here I have the integral from negative 1 to 1 of 1 over x dx. So notice that 1 over x is not continuous at 0. It's continuous at negative 1 and 1, but not at a point in the middle of that interval. So this is a case where we will have to use that third part of the definition, where I'll need to rewrite this in two pieces. So notice I'll need to rewrite this as an integral from negative 0 to 1 of 1 over x dx plus an integral from 0 to 1 of 1 over x dx. And then I can just look at evaluating one of these. Let's say I decide to look at just the integral from 0 to 1 of 1 over x dx. So notice that the problem value here is the lower one. That's the part where my 1 over x is not continuous, so I'm going to need to write this as a limit, and you can use whatever letter you want to replace that 0. I'm going to choose to use a. So I know I'm going to have to approach 0, so I'm going to have an integral from a to 1 of 1 over x dx, and then I just need to think about what direction I'm approaching it from. So remember, I got to approach my value here from inside of my interval. So notice that I'm going to have to approach 0 from the right. So this is as a goes to 0 from the right of 1 over x dx. So now we can go ahead and take our antiderivative. So we'll have log of the absolute value of x here from a to 1. We have the limit as a goes to 0 from the right. This will be log 1 minus log a. Okay. We don't know that log of 1 is 0, so I'm really looking at the limit as a goes to 0 from the right here of log of the absolute value of a with a negative sign out in front. So we want to think about our log function. So you can simply think about the log function, but if it helps, you could also sketch actually the graph of log of the absolute value of x, which will be your log function here, but reflected also over the y-axis. That's what log of the absolute value of x is. And then if we look at this, as we're approaching 0 from the right, we're seeing that our y values are getting more and more and more negative. So this is going to be negative times negative infinity, or infinity. So we found that this second part here diverges, okay, which is going to mean that the original integral we were interested in also diverges. Okay, so we can say, so the integral from 0 to 1 of 1 over x dx diverges. So the integral from negative 1 to 1 of 1 over x dx diverges. And that would be our conclusion. So just to contrast this with something that we might have tried to do before we knew about our improper integrals. So note that if I tried to do something like the integral from negative 1 to 1 of 1 over x dx, just kind of blindly try the fundamental theorem, I would have gotten log of 1 minus log of the absolute value of negative 1. Well, I would have gotten 0, but we know that in fact this integral is said to diverge. So this would be not the correct method to go about. So you got to be careful. These are kind of the type that's trickiest to see that they're improper, because you look at the endpoints and you say, well, my function's defined at both of those endpoints, it seems fine, but I got to realize that maybe there could be some kind of problem value in the middle. So I want to be thinking about the domain of my function and make sure that my function's domain includes all the values in my interval. Otherwise, I need to think about breaking it up into some pieces and using an improper integral. Okay, so let's look at a couple more examples. So here I have an integral from 0 to 8 of 1 over x to the 1/3 power, or the cube root of x. So what's the problem value here, so to speak? Okay, well, I know that this function here would have a domain of all real numbers except 0, and I do have a 0 value there. So I kind of think of this as my problem value. That's where my function here is not continuous at 0, so that's why it's going to be improper. So I'm going to have to replace that lower bound with some variable. Let's say a here. So I'm going to be looking at the limit as a goes to 0 from the right of this integral from a to 8 of x to the negative 1/3 dx. Okay. So now I need to go ahead and do my antiderivative. So this is going to be x to the negative 1/3 plus 1, or to the 2/3 divided by 2/3, or 3/2, evaluated from a to 8. So I'm going to have this limit, a goes to 0 from the right of 3/2. I'll have 8 to the 2/3 minus a to the 2/3. Okay, so now I think about taking the limit and using our limit properties here. I can do the limit of a sum is going to be the sum of the limits. So for the first part, the limit will just be that constant times 3/2. So what about the limit as a goes to 0 from the right of a to the 2/3? Well, whenever it makes sense for me to just plug in the value and I get something that's defined, that will be the limit. So since if I just plug in 0 into a to the 2/3, that's 0, this limit will be just 3/2 times 8 to the 2/3. So notice that 8 to the 2/3 would be the cube root of 8, which is 2, squared, which is 4, and then times 3/2, I'm going to get 12 over 2, or 6. Okay, so we found that this integral actually converges. And we can actually say that it converges to 6. Okay. So we saw that our integral from 0 to 1 of 1 over x dx was something that diverges. Here we have this integral from 0 to 8 of 1 over x to the 1/3, and that's actually a convergent integral. So let's look at another example. Just so we can see a variety of functions whose integrals we might be taking. Now I've got an integral here with a trig function, so I got to think about the domain of my trig function here. So I'm looking at the integral from 0 to pi over 2 of tangent of theta d theta. Remember that tangent of theta is periodic and has vertical asymptotes in the first piece between negative pi over 2 and pi over 2. So here's part of what our tan x function looks like. We know it'll keep repeating like that. So what's the problem value here on the interval from 0 to pi over 2? Well, pi over 2 is the problem value because we know that tangent of pi over 2 is undefined. Remember that tangent is sine over cosine, and cosine of pi over 2 would be 0, so we know we can't divide by 0, so that's why we have to worry about this pi over 2 value. So that's an upper value here that I have to deal with replacing. So I've picked my favorite letter. Like I said, I often just choose A for a lower bound and B for an upper bound, but you can choose whatever your favorite letter is. So I need to be looking at this limit as B is going to approach pi over 2 from a certain direction. Remember, I'm approaching it from inside the interval, so it looks like I have to approach pi over 2 from the left. So I have this limit as B goes to pi over 2 from the left of the integral from 0 to pi over 2 of tangent theta d theta. Okay, so this relies on me being able to know my antiderivative of tangent of theta. Okay. So let's see here. Let's use the form where I have negative log of the absolute value of cosine theta. Okay, it'll probably help me to think about what's going to be going on with this form instead of with log of absolute value of secant theta, but we know either one of those is the correct antiderivative. And I'm evaluating this from 0 to b. So I have this limit as b goes to pi over 2 from the left of negative log of cosine of b minus negative log of cosine of 0. Okay, remember that cosine of 0 is equal to 1. Log of 1 is 0. So we're really just looking at our limit as b goes to pi over 2 from the left of this first piece. So I have negative log of cosine of b, okay, because we know that this is log of 1, which is 0. Okay, so now we have to think about what's happening here. So let's think about our cosine function. We have to figure out what's going on with cosine b as b goes to pi over 2 from the left, and then we can think about what's happening with log of that function. So if we think about our cosine function, okay, well we know that for cosine of 0 we're at 1, cosine of pi over 2 is at 0, and then it's going to go down and come back up again, so this is at pi over 2. So if we think about what's happening with cosine x here, as we get closer to pi over 2 from the left, we're getting closer to 0, but we're approaching 0 from above. Okay, so notice that the limit as b goes to pi over 2 from the left of cosine of b is going to be a small positive number. Okay, so I have something then inside of my log function here that's a small positive number. Well, think about our graph of y equals log of the absolute value of x, which we know looks like this. So I have the inside part here being a small positive number. So as I get closer and closer to 0 here from the right on the log of the absolute value of x function, I'm getting closer and closer to negative infinity. So this is going to be negative times negative infinity, or positive infinity. Okay, so in this case we'll have to say, so the integral, okay, just to remind ourselves, this was the integral from 0 to pi over 2 of tan theta d theta that we were talking about. That integral must diverge. Okay. One other way to think about what was happening with the cosine function here is to think about the unit circle and think about b approaching pi over 2 from the left means an angle that's just a little bit smaller than pi over 2. Okay, but that still puts you in the first quadrant, and cosine in the first quadrant is positive. So we'd be getting closer and closer to a cosine value of 0, but it would be a small positive value there. Okay. If you need to review some limits, you might want to check out sections 2.2, 2.3, and 2.6, and let me know if you have any questions.